Alright, so today I'm going to be talking about a math skill that you can actually use in real life. It's not just like on paper and then it has no other use. You can actually go out and use this in a real world situation and it'll work out. So what I'm talking about is optimization. My goal for today is to teach y'all about optimization, which is essentially a equation that you're plugging in either a maximum or a minimum value, and it should work out. I learned about this in Mr. Cheatham's class. It's an AP calculus class that I took back at Cooper my senior year. So what I'm going to teach y'all is how to look at the problem right here, set up the problem, then take a derivative right here, and then the derivative end up being for a maximum value. So the question I got up here is from a YouTube video. I ended up changing the numbers around just so it would be a little bit different. So we are building a fence for a farmer to let some of his animals graze in. He has given you 600 feet of fencing and wants you to build the fence alongside his river. He wants you to enclose the maximum area that you can enclose in this fence with 650 feet of fencing. So the first step that we're going to end up doing is we need to find our constraint. A constraint is some kind of limitation that's placed on these real life problems so it actually makes it solvable. Without having a constraint, you wouldn't be able to actually do this whole equation. So our constraint is 650 feet. That's just how much fence we have, so that limits how much fencing we actually have. The next thing we're going to do is we're going to take our area. So you're building a rectangular fence. You have x is designated to this value right here. Since it's a rectangle, it's going to have to end up equaling the same thing. This side is going to be your 650 minus these two sides together. So you get 650 minus 2x, and area for a rectangle is just length times width. So times another x. Just to reduce it down and make it easier, I ended up multiplying the x out inside, and that gets us our area equation and completes step one. Step two is taking the derivative. So when we take the derivative, it's essentially on this right here, we're just going to drop the x value from 650 and we're going to get our exponent, multiply it by the number in front, and then drop it down to 1. So it just ends up becoming 650 minus 4x, and that will be our derivative. A derivative is essentially an equation that tells us the slope of a line. So we're using this to try and pinpoint exactly where we will be using the most efficient amount of fencing on our x value while also having the highest amount of area inside of our equation. The next thing we're going to do is find a critical number, and a critical number is just whenever you set your derivative number, or your equation for the derivative equal to 0. When we do that, we end up getting x equals 162.5. Our next step is just going to be testing out to make sure that it is actually a maximum value, which is what we're looking for, and not a minimum value. How you would do that is you set up this little number line right here and you put 162.5 in the middle. You put 0 and what other number you want on this side, and you're going to have these are going to be your limitations. So for us, I used 1 and 180. When you plug 1 into your derivative equation, you get a positive number. So it means the slope is increasing. When you plug in 180, you get a negative number, which means the slope's decreasing. So that means at 162.5, you reach a maximum point. So now we know our 162.5 critical number is actually a maximum. The final step that we're going to end up doing is plugging it back into our original area equation and finding out the maximum area that we have. So when we do that, we end up doing 650 minus 2 times 162.5 times 162.5, and we end up getting 52,812.5 feet squared. So that right here tells us the maximum amount of area that we can enclose with 650 feet of fencing. And then if you want to do a little bit of extra work, you could find out each side is 162.5. This side down here is 650 minus 2x. So if you plug in 162.5 for your x, you get 325 feet, which ends up adding back up to 650 feet. So you know you've done the problem correctly, you've used the right amount of fencing, and yeah. So I hope y'all know how to do optimization and solving. I showed y'all how to set up the problem, take a derivative for a maximum, and then plug everything back in together to get your maximum area. Thank y'all for y'all's time, and I've enjoyed all of y'all's speeches.